Hello there, I'm Carla Hyman. I'm your musician, comedian, and a former research scientist, and welcome to the second episode of Laboratory. Today's topic is PCR testing. PCR testing, a topic suddenly popular on the media due to the most famous virus in the world. A lot of misinformation, misconception about it, so I decided to make this video and explain you how the fuck it works. So, what is PCR and how does it work? Well, basically PCR is like a photocopy machine for any sort of genetic material, be it DNA or RNA. Now, what does PCR stand for? Because scientists love these sexy acronyms. It stands for the so-called polymerase chain reaction. There are two fundamental types of PCR, the standard PCR and the so-called real-time PCR. I'll explain both of them. Let's start with the basics though. So how the reaction works. In a PCR reaction we have the magical DNA copying enzyme called the polymerase, we have a pair of search tool devices called primers, and then we have machines called thermocyclers. And what does that actually mean in English? Polymerase is actually DNA polymerase. It's an enzyme that copies DNA on and on and on. It's a photocopy machine for DNA. How do you tell enzyme what to copy? Let's say you have a book and you just want to copy one page. How do you tell this enzyme, hey, go to that page, copy that phrase? For that, we have some sort of a molecular word search tools, which are called primers. Primers are short sequences of DNA, like 15 to 22, 25 letters long. Imagine a word search tool, because that's the easiest analogy. If you want to fish a book and a particular phrase in the book, you'd have to use 20 letters at the beginning of the phrase and 20 letters at the end of the phrase that are going to pick up this particular segment that you want to copy out of the entire fucking library. So when you make these primers, you kind of have to make them as unique as possible. Yeah, you have to really target what you want to see. Otherwise, you're going to pick up shit. And we'll come to that point later. Now, what are thermocyclers and why do we need them? Thermocyclers are basically thermostats. You know, like those thermal baths that you use in the kitchen to melt the chocolate or whatnot? Same shit, just super quick when it comes to changing temperatures. They're able to switch the temperature from 30 to 95 to 60 to 40 within split seconds. Now, why do we need this temperature variation? Well, because different phases of PCR reaction happen at different temperatures. And I'll explain it to you now, step by step. So, step number one, template denaturation, or in English, DNA comes as an infamous double strand, and we have to open these strands to be able to copy them. You know, it's basically opening up your book and saying, hey, copy here. You know, it's a bit like a girl sitting all nice and prude with her legs tightly crossed, and then you heat the temperature up and suddenly the legs fly open and the pussy jewelry is available to everybody. So that's what we do at 95 degrees. We heat up the DNA until it spreads open. Ta-da! That's the step number one. It lasts about a minute. DNA is quick to give it away. Step number two, we drop the temperature anywhere between 45 to 62 degrees. Why? Well, you see our little search tools, the primers, they are nothing but tiny, tiny pieces of DNA, like 20, 25 letters long, yeah? And they're not nearly as sticky as a long piece of DNA. So when we drop the temperature, what we want to do is have them stick to the template exactly at the spot where they should stick. Exactly there. Go find that word and sit on it. You know, they're a little bit like a short piece of a Velcro tape. You can really rip them off easily. So at 95, they're basically just swimming around in a test tube. But at 45 to 62, they attach to the template, yeah? And then, ta-da, we come to the magic extension phase, meaning once our little search tool Velcro shits are attached to the DNA template, we lift the temperature to 72 degrees, and then our DNA polymerase almighty comes into play and copies the DNA. And how that works like is much like a zipper. Check this out. This is how the extension phase works. This here below is your DNA template. It is the phrase that you want to copy. One single long DNA strand, this thing here below, okay? And now, this thing here, this is your primer, a tiny little piece of DNA sticking to our long template, telling us where to start the copying process. And this here, this is your enzyme. This is your DNA polymerase. So what does the enzyme do? It extends the primer. Oh no, my foreskin got... extends the primer and makes a long copy of your target DNA. That's it. It zips it up. So at the end you have one long piece of DNA at the bottom, which is your template, and one long piece of DNA on the top, which is the copy that you just made, which has the primer at the beginning, and the rest is what your enzyme copied. Yeah, there you go. Amazing, right? These are proper molecular tools. And now the chain reaction part kicks in. We repeat this cycle of spread the legs, attach the primers, copy, spread the legs, attach the primers, copy for about 25 to 30 times. The good part is, every time we repeat this cycle, we have twice as much as DNA than in a previous one. And it's called an exponential reaction. And I'll explain this in detail a little bit later when I'm talking about the real-time PCR. So now, we basically Xeroxed our DNA into millions of copies. Now we have to detect it. Most simple detection of DNA is the so-called gel electrophoresis, and yes, scientists love long, hard, complicated words, but it's actually simple. Gel electrophoresis are those famous pictures of DNA with kind of like fragments on a black background that everybody knows. That's the outcome of a gel electrophoresis. So how does it work technically? Well, first of all, we literally make a gel, an agarose gel, which is the same agarose that vegan people use instead of gelatin in the kitchen. I hate both. Lab traumas. Now, this agarose gel is a really porous substance. What does that mean in English? Well, if you've ever visited a children's playground, you've probably noticed those contraptions made of ropes, like hundreds of ropes all crossed between them to form some sort of a grid, and the point is to go in there and weasel through all that grid there. That's how agarose gel looks like. Now, if you ever tried to do any of those, you know that adults or chubby kids can make it only up until a certain point, and then it gets too tiny and too complex for a big person to weasel through, while the teensiest, tiniest, youngest kids just, do it and make it to the other side because they can slip through whatever crack they can find. Okay, agarose gel works the same. You take the DNA, big DNA fragments get stuck in the gel really early on, and the small ones migrate and weasel through the gel and travel at a longer distance. That's it. As you see, when it comes to gel electrophoresis, size matters. And why it matters? Well, when we copy a phrase, we want to make sure that we copy the entire shit, so we have to see that the size that we see in a gel is what we expect to see, right? And this is why we use a thing called the DNA ladder. Now, DNA ladder is called a ladder because it looks like one, and it's just a collection of DNA pieces of a known size, so we can determine the size of our particular target in comparison. It's basically like comparing the size of your own cock to a lovely collection of dildos, which, by the way, should be the only right way to measure a cock, because as we all know, cis male centimeter and a cis female centimeter are two different units of measurement without a clear conversion chart. Which makes me think that I've never heard a trans woman brag about her cock size. And that said, a cock doesn't make you a man, just so you know. Like, I've seen amazing penises attached to complete pussies. Anyway, now you see all these beautiful DNA bands glowing in the agarose gel. Well, they do not glow on their own. We have to stain them. We have to dye them first in order for DNA to be visible. We dye the DNA with ethidium bromide, which is one of the most toxic cancerogenic substances on planet Earth. Ethidium bromide is a so-called intercalating agent. And what does that mean? Let's use a zipper metaphor again. Ethidium bromide basically goes in the middle of your zipper between the teeth, and gets stuck in there. And it makes your DNA visible at the UV light because ethidium bromide can be seen at the UV light, right? And ta-da, you have these glowing, beautiful bands. And speaking of biological shit being visible at the UV light, you know how forensic scientists say there's sperm everywhere because they see it everywhere with the little UV lamps? Sperm does not glow because of DNA. It's sperm proteins that are glowing, not the DNA. Actually, I can make a whole other video about sperm visibility in UV light, now that I think of that. Now, this is the basic PCR. There is a more fancy option of PCR called the real-time PCR. Now, what's the main difference here? Well, the real-time PCR detects the copying process as it is happening in real time. The simple PCR, you see, you have to copy, and then you have to stain, make a gel, put it in a gel, let it run, and then make a picture of a gel under UV light in order to see if there's anything in there. But the fancy real-time PCR, you detect as you go. So you don't have to do the whole gel electrophoresis afterwards. Now there's other advantages to this method. You see, the standard PCR can only tell us yes or no. Yes, genetic disease is there. Yes, he is the father. Yes, the virus is there. Yes, the bacteria is there. Or no. It is a qualitative assay. It tells the quality, positive or negative. Real-time PCR is a quantitative test, meaning it tells us how much of virus, bacteria, or whatever shit we're testing for is present in your sample. It doesn't tell us only positive or negative, but it tells us the concentration of whatever we were looking for in there, which is really important when it comes to monitoring diseases. So, how in the fuck do we detect invisible DNA with a real-time PCR while it's getting copied? Well, it's magic. No, actually it's science. There's several methods that we can use to see the DNA as it's getting copied, and it's all fucking mind-blowingly amazing. With real-time PCR, we're using special thermocyclers that can actually measure fluorescence at the same time as they're amplifying and doing all the rest. They're connected to computers, it's all super smooth. And we use different strategies involving beautiful fluorescent molecules to make this DNA visible. Now, the most simple one uses a shit called cyber green, cool name. Now, cyber green is a magical fluorescent substance that likes only double-stranded DNA. To use our zipper metaphor, single-stranded DNA, cyber green doesn't like it. Cyber green is like a kink bitch that likes to fuck only with couples. It's only into threesomes, so it sees a single guy here and says, nah. But then, when they're paired and double, it's like, oh geez, double strand, I'm gonna go sit on both of them right now. And then once it binds to double-stranded DNA, cyber green lights up like a fluorescent bitch. And there you see it. That's how it works. You get your entire test tube to glow when there's double-stranded DNA. Great. Thank you, cyber green. Now, cyber green is not the only magic that we have to make the DNA visible. There's another 2 categories of molecular magic we can use here to make our DNA glow. The so-called nuclease-dependent probes and molecular beacons. The first shit, forget the name. For the simplicity, I'll just call them TAQ probes. What are these? They're exactly like the primers, the search tools that we used to determine the beginning and the end of the phrase we want to copy. Now, a TAQ probe is like a search word that sits right in the middle of the phrase, in the middle of the DNA that you're copying. And that's not everything. TAQ probe also has a molecule attached on each end. One of them is called the reporter, and the other one is called the quencher. So how do these work? All these probes use a phenomenon called fluorescent resonant energy transfer, which I know sounds like a bunch of hippies with fluo paints on their faces getting high on LSD on some techno festival, but actually it's much cooler than that. You see, reporter is a molecule that would otherwise shine, but it cannot because it's chemically bound to a quencher. This is like a highly dysfunctional marriage between a normal person and a sociopath. So what does happen with them when we copy our DNA? Well, this probe sits in the middle of the phrase we're copying, and as our beautiful enzyme comes and zips it up, it basically breaks them apart. It breaks them apart so the sociopath is removed from our relationship and our normal person starts to fucking glow. Yeah? Also, molecular beacons use the same technology. It's always about dissociating a normal person from a sociopath. So, because of this fluorescent magic, we're able to measure how much we're glowing in each cycle of PCR we're making. And of course, the more DNA we have, the more we glow, right? And thanks to this step-by-step measurement, we can actually calculate how much template DNA, how much of a virus, how much of a bacteria did I have in my sample. How do we calculate that? With real-time PCR, we use these lovely plots. This is the logic. When there's a very, very little target DNA in our sample, it's going to take more cycles to actually copy it to the point that they glow like shit. While when there's a lot of it, it just takes a couple cycles. And it works more or less like this. Imagine a mass production textile factory, like those that you see on fashion industry documentaries in China and India, that factory, okay? And you have endless rows of women with sewing machines, 8 women per row, and they have a task of copying a t-shirt. Now, they can copy a t-shirt by using a t-shirt as a template, right? So if you have a lot of sample t-shirts to give them, for example, 8 of them, you can give 1 t-shirt to each lady sitting in the first row. In the first cycle of production, they're gonna copy and make 1 copy of that t-shirt and pass it on to the row behind them. The second time we repeat the production cycle, you have 2 rows, meaning 16 ladies, copying the t-shirt, making 1 copy of a shirt each, and then passing it on to the rows behind them, which means the third cycle of amplification, we have 4 rows of 8 ladies copying each. And quicker than you know it, the whole factory is copying the fucking t-shirts, because we had 8 shirts to start with, right? Now, if we're in the same factory, but we have only 1 shirt, we have to give it to the first lady in the first row. In the first cycle of production, she's going to make 1 copy of it and pass it on to the next lady. In the second production cycle, we have only 2 ladies making a copy and then passing it on to the next 2 ladies. So by the third production cycle, we only have half of the first row of the factory working and all the rest are sitting idle. While when we had 8 shirts as a template, there were 4 rows of people working in the third production cycle. And so it's going to take more production cycles to get the entire factory to work. Basically, monitoring the speed of your production process tells you how much sample did you have at the beginning. And this is what we see in these real-time PCR plots. This here is a typical real-time PCR plot. In the x-axis, we have the number of cycles, and in the y-axis, we have fluorescence, aka how much we glow. This is a typical real-time curve. It has 2 lag phases at the beginning and at the end. Why? At the beginning, we have very few ladies working, and it takes a while for the production to start up. Then when the whole factory is working like crazy, we have the exponential phase, which is this super steep part of a curve. And then at the very end of it, there's the second lag phase, which is when, you know, we finished the textiles, some of the workers finished their shifts and went home. Some of them said, I don't want to work in impossible human conditions 18 hours a day for no pay. Fuck you. And they left and were immediately replaced with somebody else. But it doesn't matter in this example. The production stops because we ran out of reagents and our enzymes had enough of it. And so then we get the plateau phase again. We don't use the lag phases to see how much shit we had. We take the factory at the maximum production speed, which is, again, the very steep part of the curve, and we find the midpoint, and it tells us more or less how much samples did we start with 1 or 8 or whatever it is when it's about bacteria and viruses. So there you go, these are the basic PCR techniques, normal PCR and real-time PCR. There are many variations of these techniques. They amplify nucleic acids, meaning DNA, and in some cases RNA. There's another enzyme in play there, I'll explain it another time. However, they do not detect antigens, and I really care of specifying this because there's been so much misinformation in the media about PCR detecting antigens. They fucking don't. They detect nucleic acids. Ta-da! This is how the PCR tests work. Now, the tests that we use in the market that actually tell people if they're sick or not, if they have a certain genetic mutation or not, have to be fucking precise because we cannot allow ourselves to misdiagnose people, right? And so we come to two major issues that we have when setting up these tests, which are sensitivity and specificity. Two different problems which all of these tests incur, but can be controlled and optimized so that it really happens rarely. Sensitivity of a test is basically its ability to pick up on the tiniest possible amounts of whatever we're looking for in a sample. Now, if the sensitivity is low, it means that if we have just a little bit of a virus, just a little bit of a bacteria in a sample, we're not going to pick up on it even though the person is infected. And we're going to let them home with a negative result. So, low sensitivity means high risk of false negative results. If you remember HIV in the 90s, it took 9 months or 6 months of waiting time between a potential dangerous intercourse and actually your test being valid. It's because we used to test antibodies for HIV instead of checking for the viral RNA back then. And when these PCR tests came into play, they could pick up directly on a virus and on such a small amount of virus that it actually revolutionized the complete HIV, hepatitis B, hepatitis C testing, which is fucking amazing. This was early 2000s. Big massive thank you to all the scientists who set this up. Now, specificity. Specificity is a different problem. We need our tests to be highly specific, meaning they have to pick up exactly on that one shit we're looking for. Meaning, if we're infected with HIV, it has to pick up only on HIV. If we're infected with a novel SARS-CoV2 virus, it has to pick up only that virus, not other coronaviruses that are out there. Because there are other coronaviruses out there. I think 4 of them are human and are ubiquitously present around, and they cause other respiratory infections. Because guess what? Coronaviruses are older than fucking humans. We're the novelty on this planet. Remember that. Not them. They've been here long before us. But back to the testing. If we have a test that's not highly specific, it means that this test is going to pick up on other shit. And we may get false positive results, meaning we're sending out a patient with a false HIV diagnosis, meaning treating people when they don't need a treatment, and impacting their life in an insane way. So the ideal tests are both highly sensitive, meaning low risk of false negatives, and highly specific, meaning low risk of false positives. And the whole thing about developing tests is fine-tuning and tweaking the primers, tweaking experimental conditions, tweaking the temperatures, tweaking the cycle lengths and enzymes used and fluorophores until you get the perfect mix of everything so that the test is as robust as it possibly can be. And of course, this takes time. It just takes fucking time, which is why the whole disaster with the CDC test happened in the States. CDC released a PCR test that wasn't specific enough, and it had a high rate of false positives, possibly picking up on either contaminants or on other coronaviruses or God knows what. Anyway, false positives were due to their kit picking up on non-SARS-CoV-2 genetic material. And this is an issue when we develop things in a hurry. But thanks God, these are all routine processes. There's so many highly trained, skilled professionals working on this. And I'm going to use this occasion to give a shout out to my former colleagues from Italy, the entire team of amazing ladies working both in R&D and production. Actually, when I worked there, we were only women. They managed to put out a highly specific, highly sensitive COVID-19 test within weeks, and in Italy when it was really, really necessary to get it out there as quick as possible. You girls are amazing, and I'm super proud of you. Thank you for being there on the front lines, on the weekends, on the night shifts. I know you're working your asses off now, monitoring the whole thing, helping the labs, doing the tech support, and lots of love from Berlin from me. So this was it for this episode of Lab Oratory. I am Carla Hyman. If you are a science enthusiast or a bored quarantine masochist, please subscribe to my channel. Also, feel free to support me on Patreon. The address is here below, as well as in the video description. And until the next episode, greetings from Berlin. Bye!